This question tests your understanding of the LLE algorithm's parameters in the scikit-learn library. I'm checking whether you know how changing each parameter affects the algorithm's results. It's all about conceptual understanding, not complex math. The LLE, locally linear embedding, algorithm is a dimensionality reduction technique. It's used to map high-dimensional data into a lower-dimensional space while trying to preserve the local neighborhood structure. Think of it like flattening a crumpled piece of paper. You want to keep nearby points close to each other in the flattened version. Let's focus on the n_neighbors parameter. Increasing this value means that you consider more neighboring data points when you create the low-dimensional representation. This improves the accuracy of the embedding because you're using more information about the local structure. However, keep in mind that computing time goes up as you use more neighbors. It's a trade-off between accuracy and speed. The eigen_solver parameter chooses the method used to solve the eigenvalue problem, a crucial step in the LLE process. The choice of solver affects both speed and accuracy. A faster solver might sacrifice accuracy, and vice versa. It is not strictly only one or the other. The method parameter selects the way the algorithm creates the low-dimensional embedding. The choice between Hessian, and standard affects robustness. That is, how well it handles noisy data. But there's no universally better option. The best method depends on the specifics of your data. The reconstruction_error attribute gives you a numerical value showing how well the LLE algorithm has preserved the local structure of the data in the lower dimensional space. A low value indicates a better representation. Think of it as a goodness of fit measure. I'm exploring the parameters of the locally linear embedding, LLE, algorithm, a dimensionality reduction technique in scikit-learn. I'll be focusing on how different parameter settings affect LLE's performance and interpretation of the results. LLE aims to find a lower dimensional representation of high-dimensional data while preserving local neighborhood relationships. This is the core question. I need to evaluate the truthfulness of several statements about how different parameters influence the scikit-learn LLE algorithm's behavior. This parameter controls the number of nearest neighbors considered when constructing local linear approximations within the LLE algorithm. A larger value considers more neighbors, potentially improving accuracy but increasing computation time. I'm examining the impact of the choice of eigensolver on the LLE algorithm's performance. Different solvers have different computational complexities and can affect the accuracy of the embedding. The solver determines the method used to solve the eigenvalue problem during dimensionality reduction. This refers to the specific algorithm used in LLE for constructing the embedding. I'll be considering two methods, standard and Hessian. Each has different computational characteristics and sensitivities to noise. This attribute quantifies how well the lower dimensional embedding preserves the local neighborhood structure of the original high-dimensional data. A lower value means the embedding better preserves the original relationships. I'm analyzing the parameters used in the scikit-learn's locally linear embedding, LLE, algorithm, a technique used for dimensionality reduction. I'll be focusing on how different parameter choices affect the algorithm's performance and results. LLE aims to reduce the dimensions of data while preserving local neighborhood structures. This question tests your understanding of the locally linear embedding function in scikit-learn. You'll need to assess the accuracy of different statements describing this dimensionality reduction technique. Let's dive in. Increasing the n_neighbors parameter, which determines the number of neighboring data points considered during the embedding process, generally results in a better representation of local linearity. This is because more points are used to form the local linear approximations, allowing LLE to better capture the local geometry. However, this improvement comes at the cost of increased computation. More neighbors mean more calculations and, therefore, longer processing time. The eigen_solver parameter impacts both accuracy and computation time. Different solvers have different computational complexities, and thus, impact the speed. It's incorrect to say its impact on computation time is minimal. A less efficient solver could lead to less precise results. The choice between backquote method equals Hessian backquote and backquote method equals standard backquote isn't universally clear-cut. While the Hessian method might perform better in specific scenarios, perhaps with noisy data, it's not always superior. Often, the standard method provides a faster solution. The backquote reconstruction underscore error backquote attribute of the fitted LLE model is a valuable metric. It tells you how well the lower dimensional representation maintains the relationships between data points in the original higher dimensional space. A low reconstruction error indicates that the local neighborhood structure is well preserved. It's a useful way to evaluate the quality of your LLE embedding. I'm analyzing the parameters of scikit-learn's locallylinearembedding algorithm, which we use for dimensionality reduction. I'll explain how each parameter affects the algorithm's performance. We're looking at how changing these parameters impacts both the accuracy of the results and how long the calculations take. This is the core question. Vomsi, we need to evaluate the truth of 4 statements about how the parameters of the locallylinearembedding LLE algorithm behave. Let's look at statement A. Increasing the number of neighbors considered by the algorithm generally improves the quality of the local linear approximation. Think of it like this: the more neighbors you include, the better your algorithm understands the local geometry, leading to better results. However, using more neighbors means more calculations. It slows things down. Statement D focuses on the backquote reconstruction underscore error backquote attribute. This is a useful metric that tells us how well the lower dimensional representation maintains the relationships between data points in the original high dimensional space. A low reconstruction error implies that the embedding is accurately reflecting those relationships. I can think of it as how close the reconstructed data is to the original data. Statement B is talking about the backquote eigen underscore solver backquote. This parameter determines how the algorithm solves a crucial part of the calculation. The solver choice directly impacts how accurate the final embedding is. Different solvers might have different levels of efficiency, impacting computation time, but the accuracy of the final results is still directly influenced by the solver's choice. Statement C discusses the backquote method backquote parameter, specifically, comparing backquote Hessian backquote and backquote standard backquote. It's incorrect to claim one is always superior. The best method is dependent upon the data. While backquote Hessian backquote might be more robust in some cases, backquote standard backquote is often faster. This line simply states the topic of the analysis: the parameters of the locallylinearembedding algorithm. This is the title of the quiz section. We're going to analyze the parameters of the locally linear embedding algorithm, a dimensionality reduction technique in machine learning. Specifically, we'll focus on how different parameters impact the algorithm's performance and results. I disagree with this statement. The eigen underscore solver choice directly affects both the accuracy of the results and how long it takes to compute them. Different solvers have different computational complexities. A less efficient solver might give you less accurate results and take longer to run. Think of it like this: using a fancy, fast car to get to your destination versus using a slow, old bicycle. The car, more efficient eigen underscore solver, would get you there faster and more accurately. I'd caution you on this one. While the Hessian method might be better in some situations with noisy data, it's not universally superior to the standard method. The standard method can be faster, and the best choice really depends on your specific dataset. It's like choosing between 2 tools, a hammer and a screwdriver. Sometimes a hammer is better, sometimes a screwdriver. It depends on the task. This is absolutely correct. The reconstruction underscore error tells you how much information is lost when you reduce the dimensionality of your data. A lower reconstruction underscore error means that the lower dimensional representation is very close to the original data's structure, in terms of the local neighborhood relationships. It's a great way to evaluate the quality of your dimensionality reduction. This is true. The parameter backquote n underscore neighbors backquote determines how many neighboring points are considered when building the local linear representation. More neighbors generally improve accuracy. It creates a better representation of the local neighborhood structure. However, a large number of neighbors will increase the computation time significantly because more calculations are involved. Think of it as asking more people for directions. You'll probably get a better route, but it will take longer. This is the question that sets up the quiz about understanding the parameters within scikit-learn's locally linear embedding function. We will evaluate each statement given and determine which is correct based on our understanding of the algorithm and its parameters. I'll explain the different parameters you can tweak when using scikit-learn's locally linear embedding (LLE) algorithm. Think of these as knobs and dials you adjust to fine-tune the algorithm's behavior. This parameter controls how many neighboring data points the algorithm considers when building the local linear approximations. Increasing it generally improves accuracy, because you are using more information. But it also significantly increases the computation time, as more calculations are needed. This parameter lets you pick the method used to solve the eigenvalue problem, which is a crucial step in LLE. The choice affects both the accuracy and speed. Different solvers have different computational complexities, and some might give you better results than others, depending on your data. You get to choose between two methods, standard and Hessian. The standard method is usually faster. The Hessian method might give better results with noisy data, but it's not always better. After LLE finishes, I can check this attribute. It tells you how well the lower dimensional representation preserves the original data's structure. A smaller value indicates a better preservation of the local neighborhood structure. Think of it like a score. Lower is better. I'm analyzing the parameters of the locally linear embedding algorithm, a dimensionality reduction technique in machine learning. I'll explore how each parameter impacts the algorithm's performance and the quality of its output. This is key for understanding and using LLE effectively. I'm presented with a multiple-choice question testing my understanding of the "locally linear embedding" function in the popular Python library, scikit-learn. Each option focuses on a specific parameter or aspect of the algorithm. This parameter controls the method used to solve the eigenvalue problem within the LLE algorithm. Different solvers have different computational costs and may produce slightly different results. I need to know which one is most efficient and accurate for the task. This attribute, after fitting the LLE model, provides a measure of how well the lower dimensional representation preserves the original data's neighborhood structure. A lower value indicates a better preservation of the data's relationships, meaning that similar data points remain close to each other after dimensionality reduction. These are the configurable settings which control the behavior of the "locally linear embedding" algorithm. I need to understand each one to choose the best settings for a given dataset. This is a dimensionality reduction algorithm that tries to find a low-dimensional embedding of a high-dimensional dataset while maintaining local neighborhood relationships. It works by linearly approximating each data point using its neighbors. The output of the algorithm is the low-dimensional representation of the input high-dimensional data. I'm evaluating the algorithm's success by assessing how well it preserves the relationships between data points in this lower dimension. This parameter determines the number of neighboring data points used to locally approximate each data point. More neighbors can improve accuracy by considering more information, but it also increases computation time. This statement focuses on the relationship between "n_neighbors" and the algorithm's accuracy and computational requirements. I need to determine whether increasing the number of neighbors improves the algorithm's accuracy while remaining computationally feasible. This option compares two different methods used in the LLE algorithm, discussing their relative strengths and weaknesses regarding noise handling. I need to determine whether one method is always superior to the other. This statement discusses the impact of the "eigen_solver" on both the accuracy of the embedding and the computational cost. I need to evaluate the validity of this claim. This statement refers to an attribute of the fitted LLE model that measures the quality of the embedding. I need to understand what this attribute represents and how it relates to the goal of preserving local neighborhood relationships.